Have you ever just looked at the screen on your phone or your TV and wondered what makes it so ridiculously vibrant and thin? Well, the answer is this amazing technology called OLED. It works kind of like a microscopic light-up sandwich, and in this explainer, we are going to break down exactly how it's made. So, to really get what makes OLED so special, you first have to understand what it replaced. The old way, LCD, needed this big, power-hungry backlight that was always on, just shining through a bunch of filters. But OLED, it's a whole different ballgame. Each and every tiny pixel makes its own light. That means no backlight is needed at all. And that right there is the fundamental breakthrough. All right, so here's the journey we're about to take. We'll start with the initial discovery, then zoom way in on that magic pixel sandwich itself. After that, we'll get into how millions of these things are controlled, how they're actually built, and, this is the cool part, how they're engineered to bend. And then finally, we'll take a little peek at what's coming next. All right, first up, beyond the backlight. You see, this story doesn't start in some giant factory. It starts with a key discovery in a corporate lab that basically changed everything. The real starting point was this phrase right here. Way back in 1987, a couple of scientists at Kodak, Ching Tang and Stephen Van Slyke, published their research on efficient organic light-emitting diodes. And that discovery, that was the spark that lit the fuse for the entire OLED revolution we see today. But, this was far from an overnight success story. I mean, look at this. From that initial discovery in '87, it took more than a decade just to demonstrate the first displays. And then it took all the way until 2014 for companies like Samsung and LG to finally crack the code on mass production. We're talking about a 27-year journey from a lab to your living room. So how does it actually work? Well, that brings us to section 2, the magic pixel sandwich. We're going to zoom in, like way in, to see what makes a single point of light tick. At its core, the concept is, well, it's surprisingly simple. Every single pixel is a tiny, light-emitting sandwich made of special organic materials that are stacked between two electrical contacts, a cathode and an anode. That's it. So how do you actually get light out of this sandwich? Well, it's kind of like a three-step dance. First, you apply a voltage. This shoots electrons in from one side, and something called holes, which are really just the absence of an electron, from the other. Second, these opposite charges are drawn to each other, and they meet right in the middle, in what's called the emissive layer. And finally, bam, when an electron meets a hole, it releases its extra energy as a photon, which is a particle of light. You do that millions of times, and you've got yourself a picture. Okay, so lighting up one pixel is one thing, but how in the world do you control millions of them at once, like 60 times every second? That brings us to section 3, the brains behind the screen. The early displays used a pretty simple grid system called a passive matrix. You'd send a bit of voltage down a column and across a row, and the pixel where they crossed would light up. Simple enough, right? But this created a really annoying problem called crosstalk, where nearby pixels would glow faintly when they weren't supposed to. So the solution was the active matrix, which gives every single pixel its own personal on-off switch to hold its state and stop any interference. And that tiny little switch, it has a name, the Thin-Film Transistor, or TFT. The best way to think about it is as a microscopic traffic cop sitting at every single pixel, directing the flow of electricity with absolute precision. This little guy is the real key to high-resolution, high-contrast screens. But here's the catch. Manufacturing millions of perfectly identical microscopic traffic cops is, well, it's incredibly hard. Even tiny variations can lead to a problem called mura, which is the Japanese word for unevenness. It's what causes those annoying blotches or cloudy spots you might see on a cheap screen. So how did engineers solve this? This is brilliant. Since they couldn't make every single transistor identical, they just made them smarter. They built this incredibly complex compensation circuit. We're talking up to 7 transistors for each pixel that constantly measures and corrects for any little imperfections. And that is what gives you a perfectly uniform screen. So we've got the pixel and we've got the brains to control it. How do you actually manufacture the screen? That's section 4. And we're talking about everything from atomic sandblasting to creating airtight armor for these tiny pixels. To build up all the layers of the TFT and the OLED itself, manufacturers use a couple of, honestly, mind-blowing techniques. Sputtering is kind of like atomic sandblasting. They just bombard a target material, knocking atoms loose, which then perfectly coat the screen. Then there's chemical vapor deposition, or CVD, which is more like building with gas, where different gases react inside a chamber to form a perfect, solid film. Now remember, the O in OLED stands for organic. And just like organic stuff in our world, these materials are super, super sensitive. They can be destroyed by even tiny amounts of oxygen or moisture. This is where encapsulation comes in. It's the absolutely critical process of sealing the display to protect it from the elements. One of the cleverest solutions to this problem is called the labyrinth effect. See, a single barrier layer will always have microscopic pinholes in it, so instead, manufacturers alternate layers of different films. A water molecule might get through a hole in one layer, but then it has to travel this long, difficult path to find a hole in the next layer. This creates a kind of maze that makes it almost impossible for moisture to get to those delicate OLED materials. All right, Section 5, the secret to making screens bend. This is where OLED technology really goes from just being better to being something straight out of science fiction. Now, the process for this is fascinating because it's so counterintuitive. To make a flexible display, you have to start by building it on something totally rigid. What they do is coat a special plastic varnish onto a strong glass carrier. This lets them build all the delicate circuits at extremely high temperatures, something a loose sheet of plastic could just never handle. So you've built this beautiful, paper-thin display on a thick slab of glass. How do you get it off? The answer is called laser liftoff, and it's incredible. A precision laser is fired through the glass. The amber-colored plastic layer absorbs all that energy, which creates this intense burst of heat right at the boundary, and that cleanly separates the finished flexible display from the glass carrier. It is an absolutely amazing process to watch. And don't for a second think that flexible means fragile. The material science here is so good that these displays are engineered to be folded and unfolded, get this, over 200,000 times before showing any kind of wear. All of this technology is just incredible, but where does it go from here? Well, that brings us to our final section. The future is bright. What's next for the screens in our pockets and on our walls? Well, the work is far from over. Engineers are pushing on multiple frontiers at once. They're developing ultra-thin polarizers. Those are the layers that manage glare to make screens even thinner. They're finding flexible alternatives to the brittle conductor used today, and they're perfecting how circuits are built right onto flexible surfaces. And of course, they're always trying to make that all-important protective barrier even stronger for a longer lifespan. You know, when you stop and think about it, this journey has been absolutely incredible. Our screens have gone from these big, bulky boxes to brilliant paper-thin displays that you can literally fold in half. So the question that leaves us with is, what's next?